Alright, so the next bit is to figure out the momentum of the electron and the momentum of the proton. So if you remember, the electron's highly relativistic. So the energy momentum mass relation, E squared equals P squared C squared plus M squared C to the fourth, reduces because you can ignore the mass energy, mc squared, to E equals Cp. So that the magnitude of the momentum P is just the energy over C. But we know that the energy is approximately 200 MeV, neglecting again the rest energy because it's only a half an MeV, which is a less than a 1% correction to this number. So the momentum of the electron is just 200 MeV upon C. So for highly relativistic particles this is very easy. Now for the proton, this was the electron, we can't neglect the rest energy. So we have E squared equals P squared C squared plus M squared C to the fourth. So that Pc is the square root of the total energy squared minus mc squared squared. Now we've got the kinetic energy, not the total energy, so you don't stick it in for E. What you do, well, the way to do it algebraically, which I always prefer, is to write that E equals T plus mc squared, and it's squared, so we put a squared out here, and then minus mc squared squared. When you multiply out the bracket on the left, T plus mc squared all squared turns into T squared plus 2t mc squared plus mc squared all squared, and that last term mc squared all squared cancels with the existing mc squared all squared, so that Pc is the square root of t squared plus 2t mc squared. Okay, so leaving that up, we'll erase some of this electron. Finished it. For the proton, Pc is the square root of the kinetic energy squared, which is 200 squared in MeV, plus 2 times 200 times the rest energy, mc squared, which is 938 MeV, and that equals, let's do the square root of 200 squared plus 2 times 200 times 938, and we get 644 MeV, which implies that momentum of the proton is 644 MeV upon C. There is no need to substitute in C equals 3 times 10 to the 8 meters a second. All that does is it puts your momentum in horrible units of MeV per second meters. MeV seconds per meter. You see, I can't even get them right, so don't do that. Just leave the C in grouped along with the units, as all high energy physicists do. Right, now the next part of the question is to figure out the mass of a particle produced when the electron and the proton collide. So here you've got an electron coming in, well, let's have the proton coming in from this direction, and it has a total energy of, well, it's 938 MeV for its rest energy, plus 200 MeV kinetic, which equals 1138 MeV total, and its momentum, P, we've just figured out, is 644 MeV upon C, so Pc is just 644 MeV. The electron coming in from the other direction, it has a total energy of 200 MeV. You can neglect the rest energy, it's just its kinetic energy, because the rest energy is only half an MeV, which is less than a 1% correction. Its momentum is minus, remembering it's going the other way, so you've got to put a minus sign there, you're careful with that, 200 MeV upon C, so that PC is just 200 MeV. Right, now you've got to realise this problem, the last bit of this problem's got a bit of a thorn in its tail, it's a little bit of a sting in its tail, because it turns out that you can't just add up the total energies to get the mass of the particle produced. Why? Because the particle isn't produced at rest. It can't be, because the sum of the momenta in the lab frame here is not zero. However, you can use a trick. Take the energy momentum mass relation and rewrite it as m squared c to the fourth equals e squared minus p squared c squared. Now, it's also equal to the same combination of energies and momenta in some other frame. Right? Because both of these quantities, this quantity is equal to an invariant quantity. The rest mass doesn't change with velocity, speed of light doesn't change with velocity. So the left-hand side of this equation is frame independent. But look, on the right-hand side, energy and momentum in a single frame are conserved quantities, and therefore E squared minus P squared C squared is also a conserved quantity. It's the same before and after the interaction in a single frame. But the combination of E squared minus P squared C squared being frame independent and being conserved means that we can equate m squared c to the fourth after the collision to E squared minus P squared C squared before the collision, but we can evaluate E squared minus P squared C squared in the lab frame and m squared c to the fourth in the centre of mass frame. Now in the centre of mass frame, the particle that's made out of this collision is produced at rest, so this m is the mass of the produced particle. So that means that the mass of the particle times c squared, which is its rest energy, is the square root the total energy, which is 1138 plus 200 MeV, which is 1338 MeV squared, minus the total momentum, which is 644 MeV, times C, which is 644 MeV over C times C, which is just 644 MeV squared, which is, so mc squared equals, I'll do that calculation, so the square root 1338 squared minus 644 squared. No, sorry, it's 444. Sorry. 444 squared, because you add up the momenta of the proton and the electron, you get 644 plus minus 200, which gives you 444, and you have to square it, and the answer is 1262 MeV, or the mass of the particle produced is 1262 MeV upon c squared, and you again do not have to square 3 times 10 to the 8 and actually calculate that, because the answer comes out in the correct units if you just leave the C alone and put it in with the units. Okay, so that is the end of question 4.